Psalm 19:1. The heavens declare the glory of God. The skies proclaim the work of his hands. Physics time. Space is really cool. So, if you were near the ISS in a rocket ship, what direction would you want to point your engines here at the back of your ship so that you would move toward the ISS, which right now is transiting the sun? To answer that question, we need to take a look at orbital mechanics, because when you're in space, you don't have a lot of fuel and you don't have a lot of time. You need to use both of those resources effectively. And orbital mechanics is a different sort of motion than what we're used to here on Earth. So what is orbit? Orbit is falling sideways really, really fast. As in, if you're orbiting the Earth, you're moving sideways to the tune of about 8 kilometers per second. That is blisteringly fast. Orbiting is falling sideways so fast that you don't ever fall into that heavy object, you just fall around and around it. And orbits don't need to be circular either. If an orbit is elliptical, also known as eccentric, that means the satellite, the thing that's orbiting, spends more of its time farther away from and less of its time close to that object it's orbiting. And that's our first hint. If you want to know more about the background behind that, you can take a look at some of the research Kepler did, but we'll take that as a given, and you'll see that it bears out in this awesome software we're using to try and simulate this problem, Kerbal Space Program. It's a really cool physics game if you're into that sort of thing. So we can treat the International Space Station orbit as circular-ish. We're a few kilometers away from it. We need to get to it. We need to rendezvous with the ISS. So how do we do that effectively? Well, a seemingly straightforward solution would be if we are in this ship and we accelerate towards the space station until we get closer to it, and then we accelerate away from it and slow down, then we're there, right? Well, that is a straightforward approach, but we're not moving in a straight line. We are moving in orbit. So, orbit is a little bit different. But how? Well, because orbit is moving sideways really, really fast, what do we need to do to change that sort of motion? If we chose to move toward the Earth by firing our engines away from it, how would that change our orbit? It would move our orbit sideways. Or if we chose to fire our engines away from toward the Earth so that we moved away, it would also move our orbit sideways. Neither of those really do what we want. So let's take a look at our other two helpful options. Moving faster in the direction we're traveling, or slower in the direction we're traveling, or falling sideways faster or slower. That's going to change the height of our orbit on the opposite side from where we make that burn. So if we sped up on this side, our apoapsis, the furthest point from the Earth, on the other side goes away from the Earth. Or if we slow down on this side, our apoapsis stays on the side, and our periapsis, our closest point to Earth, drops close down to the surface. So how does that change where we are in relation to the space station? Well, as we change our orbit, the amount of time it takes to complete one loop also changes. How does that change? Well, right now, if we look at how long it takes to get to the other side, that's about 23.5 minutes. If we raise that, so it's approximately circular, now it's approximately 25.5 minutes. So as we raise that further and further, it takes longer to get there. Why is that? Well, as we move around, the closer we are to the Earth, the faster we need to fall sideways to stay in orbit. Or the farther away we are, the slower we need to fall sideways to stay in orbit. But hold on a sec, you're telling me we get over here by falling slower sideways, and yet we do that by speeding up? You gotta be kidding me. Well, as we speed up here, what we're doing is we are throwing ourselves not just a little sideways, but a little away from the Earth. And as we continue to orbit, we fall further and further away, and we convert some of our kinetic or moving energy into potential or stored gravitational energy. So we end up moving slower sideways as we get further and further away. And then after we pass our apoapsis, that highest point, we pick up speed and we come back down. But the net effect is that our orbit takes longer. Similarly, if we slow down where we are now, we're going to drop closer to the Earth and pick up a lot of speed, and our orbit is going to take less time. So what that means, for us, if we are behind the space station right here, we want to fire our engines toward it, because the net effect that's going to have is it's going to drop us down into a lower orbit, so we fall closer and faster, and we complete one orbit in less time, and as we come back around, then we meet up with and rendezvous with the space station. So we can see what that looks like. We have the space station right there. We are pointing our engines toward it. We fire our engines. We watch as our intercept decreases 40 kilometers, 20 kilometers, 10 kilometers. Slow down our firing, 5 kilometers, 3, and intercept. So, as counterintuitive as it may seem, if you want to intercept with the space station and you're close to its orbit but you're not there, you want to fire your engines toward it. Now, I know I glossed over a whole lot of details, one of them being, if you're in orbit, you're not firing your engines, you're firing your reaction control thrusters, but we can talk about that another time. Thanks for joining me, and I'm looking forward to talking next week about physics.